Today we start Chapter 2. Chapter 2 talks about atoms, molecules, and ions. Chapter 2 is a pretty big chapter. We will be learning how to write formulas. Some of you that had high school chemistry already know this. And it begins with just a little bit of history on the atomic theory. And the atomic theory begins with just John Dalton, who is credited with the discovery of the atom, but it really does begin much, much earlier than Dalton. And it actually begins with the ancient Greeks, who, in theory, just used to sit around and discuss life and discuss things, and said that, you know what, there has to be something that's the smallest piece of matter. And it was a guy named Democritus that said, there has to be something that's the smallest. If you took a rock or some piece of matter and you kept breaking it down into smaller and smaller pieces, there eventually has to get a piece that's the smallest. And so it was at that time that Democritus came up with the name atom, atomos, which means indestructible or indivisible. And since that time, which was about 2,500 years ago, people started looking for that smallest piece. And then it was John Dalton that finally found what everyone thought at that time was the smallest piece of matter. And he developed what he called the atomic theory. And his atomic theory was pretty extensive, especially for the time. This was in like 1801. And he said that, first of all elements were made of these little tiny, tiny particles that he called atoms in honor of Democritus, from that Latin atomos, meaning indivisible or indestructible. He did say that all atoms of the given elements were identical. They were exactly alike in every way, the same size, same mass, same chemical properties, same everything. But that atoms of different elements were different from each other. And we know today that that's not true, but it's pretty close. He also said that compounds are made up of atoms of more than one element that are combined chemically, and that they're present in the same ratios. And we're going to talk about that a little bit more. And he also said that when chemical reactions happen, they happen because elements are joined together or pulled apart, but that they're never destroyed. We don't destroy atoms, nor do we create them. So then this guy named Proust came along, and he came along with what's called the law of definite proportions, that says if you combine these chemicals, they're always going to combine in the same definite ratio, the definite same proportion. And that's why you can't have half an atom when it combines. You're never going to have a half of an atom of oxygen or a half an atom of carbon. That just doesn't happen. You're going to have whole number ratios, even if you have different amounts in the mix. So there's this slide as an example of that. And then you have the law of multiple proportions that says even if you mix them up, that they're still going to have the same ratio. Okay, so if you were to take different compounds even, and you have carbon dioxide in this example, or carbon monoxide, that you can come up with ratios, and this is called an empirical formula, by the way, which we're going to learn how to do in this chapter, that the ratio of oxygen to carbon and carbon dioxide is 2 to 1, that the ratio of carbon to oxygen and carbon monoxide mass-wise, mathematically, is 1 to 1, but it's still whole number ratios, and it's very specific in that. So we're going to learn how to do that. And then here's a sample problem. Both water and hydrogen peroxide are made of hydrogen and oxygen. When water is decomposed, oh, by the way, I didn't tell you what page this was on in your text. This sample problem is on page 4 of your text if you wanted, 4T, if you wanted to follow along. when water is decomposed or broken down into its elements, it produces 1.25 grams of hydrogen for every 1 gram of oxygen. So if you have this 0.125 grams of hydrogen for every 1 gram of oxygen, yet when hydrogen peroxide is decomposed, it produces 0.063 grams of hydrogen for every 1 gram of oxygen. So if we were to determine the mole-to-mole ratio in that, or the gram-to-gram ratio rather, for those two things, we could find that these follow the rules right here. So if you talked about the grams of hydrogen that's in water and the grams of hydrogen that's in hydrogen peroxide, we're going to see that they still follow the law of multiple proportions. Now, I went through that very, very quickly because in my mind, this is the lesser important things in this chapter. Other things are significantly more important. However, you're going to see that still you don't have half an atom of hydrogen. You have whole atoms of hydrogen. Even though they mix in different proportions in water and in hydrogen peroxide, there are 2 atoms of oxygen and 2 atoms of hydrogen and hydrogen peroxide and 2 atoms of hydrogen and only 1 atom of oxygen in water. So, but you can still see that that it turns out to be a 2-to-1 ratio of hydrogen in water to hydrogen in hydrogen peroxide. And then here's another sample problem. If you're talking about sulfur that's in sulfur dioxide and sulfur that's in sulfur trioxide, and we're not even going to go through that one. Okay? Section 2.2. In Section 2.2, this is talking about more structure of atom, because we went along, I wasn't there, by the way, from 1801 all the way to 1897, thinking that John Dalton was the man. He had discovered what he thought was the smallest piece of matter in finding the atom. Now, there were a lot of discoveries made in the 1800s. So many discoveries were made during that time. Many important elements were discovered. The periodic table was set up during this period of time. So much important science was done. But for a long time during this period, it was thought that the atom was the smallest piece of matter that there was, until the discovery of the electron. And then so many discoveries followed very quickly after. Radioactivity, the proton, the nucleus, so many others. But the model of the atom morphed tremendously into what we now think that it looks like. And yet, I personally think that there's some still flaws in what the current model looks like. And my biggest problem with it is that I can't visualize it. But some of you art kind of people maybe can. So let's talk about, quickly speaking, the discovery of the electron. The discovery of the electron was made by a guy named J.J. Thomson. No P, just Thomson with no P in his name. He was shooting some very high-speed particles through a cathode ray tube, which is an evacuated tube. It didn't have any air in it. And he was just passing them through a current. He wanted to see what was going to happen. And the unexpected happened in that the ray bent. He was not expecting that to occur. And so he had to ask why. When he had a positive and negative charge there, why did the light bend towards that positive end? And the only thing that he could assume from it was that those particles must have some sort of charge, and hence the electron was discovered in that way. And here's some pretty cool pictures of it that are also in your textbook. And those pictures are on page 42 of your textbook. That kind of goes through that discovered from J.J. Thomson. And then right up under that, you see very, very quickly after that, that Roten then discovers radioactivity and how that all came about as well there. And I'm not going to go through and ask you to know the charge to mass ratio of the, that's a typo, that says ration and it's ratio of the electron. And even though the Millikan drop oil experiment was hugely important, and that is the mass of an electron, then 9.10 times 10 to the negative 28 grams is the mass of an electron. I'm not going to ask you to know that. However, it does help you with conversion factors later on. So, but I am telling you, I'm not going to do any problems or anything with that because that's not one that I'm going to ask you to know. All right? But this is how radioactivity was discovered and how it works, actually, and it's outlined for you on page 43 of the text, and how it all came to be. And they're called beta particles or beta rays if they get shot out of the nucleus. And then you have gamma rays and alpha particles. Now, we are going to have an entire chapter devoted to this, and I'm very seriously thinking, I told you I might switch some things up. We're supposed to have chapter 5 as part of our midterm. I may swap that out, especially now that we're getting into this chapter more, and it's talking about alpha particles and beta particles. Chapter 20 is the radioactive and the nuclear chapter, and I may choose to swap it out because it kind of goes along with this, and it's, plus it's the easiest chapter in the book. So I may do that before our midterm and have that as part of it. So the most famous of all, and one of the most important discoveries of all, was the discovery of the nucleus. And it's one of the most famous of all of the experiments because Ernest Rutherford was an Englishman, and he was an instructor at one of the most prestigious universities in all of England. And he developed this cool-looking experiment called the gold foil experiment. And he was at Cambridge. He was just so important, and he developed this experiment to try to capture what a photograph, I guess, sort of light particles or particles hitting this new fangled photographic type film. And he thought that if he took these alpha particles, which was basically a laser beam, a very early model laser beam, and he thought that if he shot it at this horseshoe-shaped structure that he made, that he lined, and this is all in your textbook, by the way, he wanted to see what they might look like. And there was the new film that was developed, and he thought that if they shot the particles at it, that it might go through. So they wanted to slow them down. So they decided if they shot them through something like gold foil, which is like aluminum foil only made out of gold, that it would slow them down enough and they could capture these pictures. And what they expected to happen is they expected the alpha particles to shoot through the gold, as you can see. Let me get a pen to write with. Right up top here, they expected these particles to go right through because at this time electrons had been discovered, but they thought that the rest of the atom was kind of like a doughy mass, sort of like I would think of it as chocolate chip cookie dough before you added the chocolate chips, just really gooey and doughy. That's kind of what Thomson's idea of an atom was. That it wasn't really hard, because that's what Dalton thought it was. It was like a BB or a marble, super, super hard and indestructible. But when Thomson came along and he discovered the electron, he thought that an atom was more doughy than it was hard. So Rutherford, who studied with Thomson, he said, okay, let's shoot these through there. And he thought, well, they'll get slowed down as they go through these gold foil, and we can get a picture of them. So that's what he decided to do, and yet when they shot them through these gold foil, they did not do as expected at all. He thought they would go through and they'd get little flashes of light on the other side, and they'd be directly opposite, but that's not what happened at all. They shot all over everywhere, and instead of hitting directly across right here on this side, just like they thought, they came and they hit. Some of them ricocheted straight back, some of them ricocheted here, and they thought, why in the world is this happening? And at first they thought it was the flaw in the operator, which was not Rutherford. He had one of his assistants do it, and then they did it a second time, and then finally on the third time, Rutherford was there also and said, well, why is this happening? And they said there must be something small and tiny and really dense in the middle, and it has to be positively charged. And lo and behold, there's the nucleus, and inside that nucleus must be protons. And shortly thereafter, the neutron was also discovered. So there you have. So now we have atoms are positively charged, have these protons, that are positively charged, and then they're all live in this nucleus, and it's very, very, very dense and very, very tiny. It has to be very tiny because most of those alpha particles that they shot with the laser went straight through. It was only a few of them that got deflected. So he reasoned that that nucleus with the positive charges had to be pretty small. That's what he said. And then he called them protons. And then Chadwick came along, and he then discovered neutrons, and he said they also live in the nucleus. And he said they're neutral, and they live in that nucleus, and they're just slightly larger than the proton, and their job is a tough job. They have one of the hardest jobs, I think, in the atom. Their job is to hold those protons, because protons are positively charged, and they're all living there together. So especially for the heavier atoms, their job is to hold those protons tightly in place, to bind them together. And so this is a picture here of what, how tiny the nucleus is, and the protons and the neutrons together inside that tiny nucleus. And then you see that kind of cloud. That's where the electrons are roaming around, making a cloud of negative charge. Okay, so here are your three particles: electrons, tiniest mass, then you have protons and neutrons that are only slightly more massive. Protons and neutrons live in the nucleus, and the electrons form clouds of charge as they are spinning and flying around outside the nucleus.